Hello, my name is Cal Coolum for anyone coming back and watching this VOD. I am your personal modern fantasy physics tutor, but today, instead of a lesson, I'm actually going to be doing some of my own physics research because I have a meeting tomorrow and I need to get some more done. So, here I have a Mathematica notebook. So, Mathematica is a program that basically does algebra for you. And because that is the most tedious part of doing any physics, I am going to let my computer do it. I already have this started. I'm trying to calculate some matrix elements. First thing I need to do is go through and calculate the matrix elements in the conventional case before I do it in the weird case that I'm studying. So matrix elements are basically just these numbers that give you information about, in this case, a scattering process. In particular, for my case, polarized electron-photon scattering. This is also called Compton scattering. And in the case that I'm using where I have really high energy electrons, this is called inverse Compton scattering. So let me just change some stream settings real quick. All right, better. Okay. So the first thing I need to do now is make sure that I have the correct expression. So I did some handwork earlier here. I need to make sure I have the correct expression for that. So the one that I have was omega 0. So omega 0 here is the incoming energy of the photons times the square root of p squared plus m squared. This is the energy of the photon plus the momentum, or sorry, the electron plus the momentum of the electron times the cosine of the angle theta 0. This is the incoming angle of the photon. So if we have here, I'm assuming that the electron is propagating down the z-axis, and so there's going to be some angle of attack that the photon has while coming at that I'm describing. Oh, sorry, I changed it. It's actually theta 1, not theta 0. In fact, I probably need to rerun this, don't I? So that I can be consistent. I'm just copying and pasting this expression right here. And then in the denominator of this fraction, we have, again, the energy of the electron, p squared plus m squared all square root. And now we have minus the momentum times the cosine of the outgoing angle, so theta 2. And then plus the incoming photon energy times 1 plus, this is the part that gets hard to remember, so it's cosine theta 1 times cosine theta 2 plus sine theta 1 sine theta 2, and then last times the cosine of phi 1 minus phi 2. So this is the azimuthal angle for our photons. This part isn't as important, and hopefully in all relevant results that come down later, we should no longer see this phi dependence. But it is there just for this most general step. And so what I want to do is make sure that the output of this expression that I found here, the W2 goes to this, is the same as this expression that I calculated by hand. So this was the output. I'm subtracting off what I calculated by hand, and if they're the same, this expression should go to 0. and then I have it inside this full simplify function. So, and taking a second to run is not a good sign. Usually, if this is going to evaluate to 0, it'll do it pretty immediately. So, okay. So yeah, something's going on. Because this should have gone to 0 pretty quick. Oh, I just realized I didn't change the title on my... Gosh. Let's spell research right. And there we go. How does that look? That's fine. Okay. Still no output here. Ah. I didn't change this back to P1. So, just to keep everything consistent, I decided to change like this P to P1 because I was denoting the vectors here, like P1 for the incoming and P2 for the outgoing electron. So hopefully if I change all those P's to P1s, abort the evaluation, and run this again, we should see 0. And this becomes omega 1. It's very difficult to change notation in the middle of a problem that you're working on. Did I actually abort that? Yeah. All right. Let's see. Still not completing. Just get rid of this. Okay. It's frustrating because I know that this is the right result, but I want to make sure that like it's being calculated properly, you know, from the very beginning, because when I go through and I want to change some of this in the future, I want it to still give the right result. So what I'm going to be changing in the future, I am going to be putting a modification to the electron dispersion relation. So instead of this just being the square root of P1 squared plus M squared, it's going to have some correction to it that is going to be some small perturbative thing. So we can just linearize everything with respect to it and hopefully get some kind of modified result to our cross section. I already know that the kinematics will get a modification, but if the cross section does too, that'll also be a signal that we can look for. Because what I'm doing is trying to search for this modification, this correction to the regular solution to the problem. All right, still running. Not a good sign. Let me just... Okay, let's maybe just move this out of the way for a second. Take this expression that it gives us. Oh, I need to abort first. Okay, yeah. So if I just, obviously, if I take something and just remove it, then like it's itself, then obviously we're gonna get 0. And maybe I'll just try to hand simplify this for a little bit. So just divide out the 2's. So this will get a 1/2. Remove the 2 there. 1/2. And remove the 2 there. And then we just get rid of this whole 2 right there. And we still get 0. Okay, just what we expect. And maybe me okay. Still too long of an expression for it to put it as like a fraction with like a full line across and rather than just a slash. But okay. Let me factor out an omega 1 in the numerator. Hopefully that'll put it more in the form that we have here, because you can see that we have this omega 1 factored out here. So just get rid of that. Okay, still the same. Now, okay. So now we have omega 1 times, I'll factor out this omega 1 again, 1/2 minus cosine theta 1 squared for 2 minus cosine phi 1 squared, and then times sine theta 1 squared. Okay. Now, oh, I see what's happening. So if we have phi 1 is equal to 0, then this, oh no, this expression won't go to 0 because there's no factor of 1/2. So I'm missing that somewhere. Did I put these inputs incorrectly? Yeah, I believe so. Because we have this one coming. So we have like first the electron propagating down the main line on the z-axis. So this first input here is your energy. The other 3 below it are your x, y, and z components. So if I have the electron coming down the z-axis, we then have the photon coming at it, like in that same direction. So we have a small theta 1. I think theta 1 is about 1.5 degrees for the experiment that I'm working with. Cosine shouldn't matter, but I want to put in like the dependence just because, just to make sure that it cancels out. But yeah. So we have, I see what I did wrong. This has to be sine. Yep, I think that's what did it. We have this here, new expression here, Control C, take this, Control V, subtract off the expression that I know should be the right answer for the conventional case, and we have 0. Exactly. All right, cool. So it's really important to do these kind of like sanity checks when you're doing research. Like, make sure that you're getting the right answer, always check your results. So my advisor, he has Mathematica documents where he like knows that he has like the right forms of the gamma matrices plugged in, but like, so that's these matrices here, but he'll still check to make sure that these set of matrices satisfy what's called a Clifford algebra, which is kind of what defines the properties that we want to have for these matrices. These matrices are very heavily related to fermions, so like spin 1/2 particles. Okay, so now that we have that, now I want to go through, and we're doing like this polarized scattering, so I want to, instead of summing over the photon polarization states, I'm going to pick one of these two and input it into the calculations. But the issue being is that the photon is not going to be directly down the z-axis. It's the electron that's going to be down the z-axis, and so we want these left and right polarization states to be actually along the axis of the k1 and k2 vectors. So I need to figure out how to do that. And maybe it would be better to just go ahead and also do the like electron spinners solutions. So the spinners, what would be the best notation for that? So we need a spinner coming in. For the P1 momentum state, so maybe I'll call that U1. Yeah. I'll call that U1. So this is a spinner that's coming in. With momentum P and spin state S. So, let's see, I chose the while basis for this. So maybe I need to look at what the solutions for the spinners and the while basis are. I guess I could also just write out the Dirac equation and do like the eigenvalues of that. Yeah, maybe. Let's do Dirac equation, or maybe Dirac operator. Because the Dirac equation is technically just the Dirac operator applied to your state, and that should be equal to 0. But right here, I just want the Dirac operator. And I'll specifically call this Dirac operator 1, because the Dirac operator is going to be a function of the momentum, and since we have two different electron momenta that we're concerned with here, the incoming and the outgoing states, I will have two different Dirac operators. So let's see, for this one we have, we're going to sum over mu. Oh, one sec. I got rid of one of the things. So we'll sum over mu is equal to 1 to 4 of P1L. So this is to indicate that it has a lower index. That is important when you're doing these kind of summations, that whenever you're summing something, you want something with one lower index that I denote with L and something with a upper index, which I'm denoting with U. So that's this gamma matrix here for in this case. And then minus M, and we need this to also be a matrix valued term, so I multiply it by the 4-dimensional identity matrix. So if I just do matrix form, Dirac op 1 should be, objects of unequal length. Oh, I did something wrong. Uh, this is the right notation. This should work. Let me try something. Let me just instead of multiplying by it, just okay. So it knows what I mean when I say to sum over this stuff. Yeah. And so if I say P1L mu, and now it doesn't know. Does it think that this has more, that the P1L has more indices than it actually does? Oh, let me try this. So maybe that's what'll fix it. Or if I do a matrix form P1L. Okay, so that's the right number of matrices, the right number of indices, but it's also getting it right if I don't do that. Okay. I've run into this issue a lot, and I don't quite understand what the problem is. But sometimes if I just like re-express things in different ways, the problem goes away. But I'm not entirely sure of why yet. Because yeah, it should be taking the first element here, multiplying it by the first matrix. So like if I maybe let me just try something. Just make it like a random vector. In fact, why don't I make it something like this, or A and B, how about that, rather than 1 and 2. Make this R mu. Okay, so it still has that issue. Okay. I guess I could just do it out the long way. So Dirac operator 1 is equal to sparse array. And then I need it to be a 2-index object, so there. And now I just put this inside a do function. And now we have we'll call this A, B, and B. Let's get rid of this. And so we want to do this for every value of A and B, so that's 1 through 4. And we need to replace this back with P1L. Okay. Yep, that's what we want. Oh, but it is still not interpreting the right number of. Uh-oh. No. I need this inside. Here. Not here. And this needs the 1. Yeah, okay. Cool. So that's the first Dirac operator that we want to deal with. And I feel like this one's going to be a lot easier to deal with than the outgoing one. So the outgoing one might actually be simpler because I think we can still average over the outgoing states. So I don't necessarily think I need to find the exact spinners for that one. Okay. And so now we want eigenvectors of the Dirac op1. And okay, maybe and let's maybe just select out one of these. Put it in a matrix form so it's easier to read. Yeah, okay. That one there is interesting. I was not expecting that. Probably because it isn't normalized. But, so let's take this outside of the matrix form. Call this U1. We can normalize it later. Hmm. Let's drag off one. Dotted into U1 minus. And that should give me 0, right? No, it does not. Hmm. Sorry, responding to a text real quick. That's not what you want. It should have a 0 eigenvector, unless... Oh, it's because I didn't ensure. No, it should still be a solution to that. There should be a 0 eigenvector. I'm doing something stupid. I feel like I'm overlooking something simple. Well, by the way, maybe I should just come back to it because I also need to put this in the right form. So we have to have a correction to this. And then I've been using, so there's positive and negative corrections to the energy states depending on which state is incoming to the scattering. And so what I've been doing is denoting whether that's a positive or a minus sign just with this C1, and I'll do a C2 for the next one. So times P1 times H. H is going to just be a function that depends on the direction of the apparatus, so you should see some kind of variation as the day goes on. But here, this is just a low term, so like we get a linear correction. H is supposed to be like perturbatively small, so we should still see something very close to the original case. And maybe it's in here. Yeah, maybe I'll actually split up the three momenta from the full thing. So we'll do J is equal to 2 to 4, so we only select out the last 4 of these components. I guess the last 4 of these components here. Last 3 of these components here. I guess it'll technically be for this P2. So we have P2U, J, P2L, J, plus M squared. So this, and then plus C2. And then we will again have square root and we'll see Control V. This time times H again. minus all this minus P2 U1. So we select out the first component of it. So now let's see what we get. This might take a little bit more time to run than the last one. Yeah, so we can see we have this correction to your conservation of energy here. Well, I guess I should have told it to only go to linear order in H, but oh well. We're going to get some expression and then we can Taylor expand that in H. Yeah, I wonder if there's any way to like tell it to solve something only to linear order. Let's see, because where else is it gonna show up? So P2 has something that's linear in H here. I guess what I could have done is replace this here with the 0th order correction to it. Yeah, maybe I'll abort the evaluation and do that. So we'll do series. Maybe so I'll call this P2 U 0. So it's the 0th order. Or maybe P2 U, or maybe P2 Li for, so just like a quick note, like these corrections break Lorentz symmetry, so we call them Lorentz violating. If we remove the like breaking of the Lorentz symmetry, we call it Lorentz invariant. So that's what I'll have this Li stand for. So this is the second momentum Lorentz invariant part of it, and the U is for the upper index. So we do series P2 U, and we'll do it a series in H. And I think it's like 0, 0, right? Let me P2 Li U plus order H1. Is that the proper way to use series? I want to get rid of the order H1. You can pull up. Yeah, so yeah, I because we're expanding around h equals 0. I want to get a 0th order in it. The output. So I do normal series. Forgot about normal. I need to abort again. Yeah. Okay. And I still forgot to put it into the other. So P2 Li. Oh, we don't have this, so P2 Li L is equal to eta dot P2 Liu. And so this, what this does is this eta matrix lowers the index. So hopefully this will take not as long to run. It's probably still going to take a minute because we have added a lot more complexity to this expression. I think this is the most boring part about using Mathematica, is just waiting for everything to run. Is there anything I can do while I wait for that to finish calculating? Yeah, so this is all the handwork that I've done for this. And then with all of these also filled up pages. Let's see. I was working on like calculating these matrix elements. Maybe it'd be worth it to like go through this and just try to do it by hand and then check the result at the end, because it's Mathematica finds it a lot easier to tell you that like, oh, this goes to 0 than to actually calculate something itself. So basically what we have I seem to be missing my stylus. One sec, I need to go and look for that, so I'll be right back. All right. It was exactly where I left it. Okay. So first we have what I was calling P1. I think for handwritten parts of it, I'm just going to call it P, and then like afterwards we'll call the second momentum P prime. Same thing with the K's. So this is going to be here. Maybe I'll need to give it 2 rows. So we have the square root of P squared plus M squared plus. And I'll call this let's see, S. So we know that it refers to like the spin states. And times momentum P times that H factor. And then we just have 0, 0, P for the space-like components. For the K's, it's a little bit more complicated. But we can say it's going to be omega, I'll call it omega 0. No, I'll call it omega. No, a 0 because what we're looking for is going to be the outgoing one, and I'll just call that omega. And so for this one, it's just going to be 1. And then we have our minus sine theta 1 cosine phi 1. I think actually the notation used in some of the papers for related things uses 0 index here. Theta 0 cosine phi 0 minus sine theta 0 sine phi 0, and then minus cosine theta 0. And then K prime, so this is the outgoing photon for momentum. We have, in this case, what I'll call just omega. I didn't want to put the 0 index on these 4 momenta labels because the space-time indices run from 0 to 3. And so it would get confusing about whether I was talking about like, oh, am I talking about the initial 4 momentum or am I talking about the 0th component of the 4 momentum? And so just to avoid that, I'm going to be using primes or no primes for the 4 momenta. And so for this one, we have 1. And now this one, I'm not going to have zeros on it, so we'll have sine theta 0, cosine, no, sorry, no 0, phi 0, no 0. Sine theta, sine phi, cosine theta. All right. And so then our P prime is going to be just the whatever it needs to be to conserve energy and momentum. So plus P squared M squared plus C S times P times H minus omega 0 minus, yeah, so this should be a minus 1 here, sorry. No, plus 1. So plus omega 0 minus omega. Then we have omega 0 minus omega 0 sine theta 0 cosine phi 0 minus omega sine theta cosine phi minus omega 0 sine theta 0 sine phi 0 minus omega sine theta 0. Nope, not 0. I keep doing that. Sine phi. And then lastly, we have p minus omega 0 cosine theta 0 minus omega cosine phi. No, theta. All right. And then we want this to satisfy as well the new modified dispersion relation, which is p prime 0 is equal to the square root of pre-vector prime, I guess. Maybe I'll just call that p prime. Yeah, so let me add like indices to this, just so we know that we're talking about the vectors for these. And then if it doesn't have an index, I know that I'm talking about the magnitude of the 3 vector. P prime squared plus m squared plus, let's see, s prime p prime h. And here this h is the same h that we had before. And so we need to determine what this p squared is. And I believe I determined earlier that p prime was equal to the square root of p squared plus omega naught squared plus omega squared minus 2p omega naught cosine theta. Is this one a plus? Let me see. Should be up here somewhere. Yeah, so minus. Okay. So minus for both of these. Minus 2p omega cosine theta. And then plus 2 omega naught. Maybe I'll do omega naught omega times cosine theta 0 cosine theta plus sine theta 0 sine theta cosine of phi 0 minus, or maybe phi minus phi 0 is the more intuitive way to write this. Phi minus phi 0. And then just, yeah. I don't know why I wrote that whole thing. It's just easier to do the 1/2. Okay. Now, let's determine what this is. So we already showed so for this, we also need to know what the 0th order p vector is. Which actually should be the same, shouldn't it? Yeah, because the correction only comes from the 0 component, which we're not including here. Yeah. So now we have p squared plus m squared plus cs ph plus omega 0 minus omega is equal to the square root of p prime squared. So that's going to be this right here. Maybe I should write this as p squared plus m squared plus omega naught squared plus omega squared minus 2p omega naught, this should have 0, cosine theta naught minus 2p omega cosine theta plus 2 omega naught omega cosine, and maybe I'll switch to right ink. It'll get hard to read if I have like an index on an index. Cosine theta naught cosine theta plus sine theta naught sine theta cosine of phi minus phi naught. Actually, yeah, so the m squared that I just kind of reordered it and put it there, plus cs p prime h. And I'm going to put the p prime h on the other side. So let's kind of group things together. So we have p squared plus m squared plus omega naught minus omega. So that's our lowest order on this side. Plus parentheses cs I wasn't using the parentheses around the subscript. P minus cs p prime all times h is equal to, and then we have this long thing again. All right. And now we just need to square both sides to get rid of the square root here. But we keep in mind that we can ignore anything that's linear in h, or nonlinear in h, so anything of higher order in h, so we don't have to like just square this. So what we're going to get is the square root of, or actually not the square root, so we're going to have p squared plus m squared plus omega naught squared plus omega squared. And then plus 2 square root of p squared plus m squared omega naught minus 2 times the square root of p squared plus m squared omega, and then minus 2 omega naught omega, and then we have plus square root of p squared plus m squared times c s e minus c s prime, so yeah, they should have primes, p prime times h. And this is going to be equal to this expression here. So we have p squared plus m squared plus omega naught squared plus omega squared minus 2p omega naught cosine theta naught minus 2p omega cosine theta minus 2 omega naught omega cosine theta naught cosine theta plus sine theta naught sine theta cosine phi minus phi naught. And now we can see, we can see what cancels out. So we have p squared cancels, p squared, m squared cancels with m squared, omega naught squared, omega naught squared, omega squared, omega squared. And now we can add everything over to the other side. So we'll take 2 square root p squared plus m squared omega naught minus 2 square root of p squared plus m squared omega minus 2 omega naught omega plus the square root of p squared plus m squared times CSP minus CS prime P prime times H is equal to, and then plus, I should say. We want to move everything over to the other side. So plus 2p omega naught cosine theta naught plus 2p omega cosine theta minus 2. Should that be plus? Yeah. That should be plus. So minus 2 omega naught omega cosine theta naught cosine theta plus sine theta naught sine theta cosine phi minus phi naught. And now what we need to do is group together our like terms. So I think I want to first group up, this equals 0. And so now maybe I'll put that on the side. 0 is equal to, and I'll have everything that depends on omega here. So I'll probably make this minus omega. So minus omega times, and I'll also, you can see that yeah, everything here should have a factor of 2, actually. So there should also be a 2 here. Yeah. Everything has a factor of 2, so I'm going to head and canceling all of those out. And so we're just going to be left with p squared plus m squared here. Let's look where our next omega is. So maybe I'll skip ahead to this one. So minus p cosine theta. Here we have minus omega naught. And then we have another omega naught term here. So what I'm going to do is, and this should be plus actually because we already have the negative sign out here. I'm going to combine everything that we had, those times omega naught. So we have 1 coming from here, and then we have these string of trig functions here. So that's plus cosine theta, cosine theta naught, cosine theta, plus sine theta naught, sine theta, cosine of phi minus phi naught. And so that should be everything that's multiplying omega. So then we just take everything else, And we'll separate that out into things that don't depend on h, this parameter that we're trying to expand with, and then the things that do depend on it. So starting with the things that don't, we have the ones that depend on omega naught. That's going to be this first one. We have square root of p squared plus m squared. And actually, this should have more to it than that, shouldn't it? So this should be square root of p squared plus m squared. Plus omega naught minus omega, I think. Right there? Yeah. All right. But okay, starting with the things that depend on omega naught. Then we also have minus, or no, plus in this case, p cosine theta naught. So that should be everything that doesn't depend on h. Now we have the terms that do depend on h, and it's just this one right here. That's going to be plus square root of p squared plus m squared plus omega naught minus omega times c s p minus c s prime p prime times h. And so what we can see is that omega is going to be equal to, on top we have this expression, so square root of p squared plus m squared plus p cosine theta naught divided by square root of p squared plus m squared minus p cosine theta plus omega naught 1 plus cosine theta naught cosine theta plus sine theta naught sine theta cosine phi minus phi naught. So that's our first term. Move this down over here. And then we have the next term. So plus, and now we have square root of p squared plus m squared plus omega naught minus omega CSP minus CS prime P prime times H, and then divided by that same thing in the denominator. So we have the square root of P squared plus M squared minus P cosine theta plus omega naught 1 plus cosine theta naught cosine theta plus sine theta naught sine theta cosine phi minus phi naught. And so what we can do is we can see we have here a expression for omega. It doesn't fully specify omega because we have this p prime here, and p prime itself depends on what omega is. But what we can do is, since we only want things linear in H, we can take our 0th order solution and plug it into our expression for p prime and this omega here, in order to get a linear expression for an expression for omega that is linear in H. And we can see that that is going to be somewhat nasty, but it is doable. So let's see, what will be the easiest place to start? Maybe by just writing out the full thing. So we have p squared plus m squared minus p cosine theta plus omega naught 1 plus cosine theta cosine, so cosine of theta plus cosine times cosine theta plus sine theta naught sine theta cosine phi minus phi naught. That's all on bottom, and then on top we have p squared plus m squared plus p cosine theta naught. And now we have plus square root of p squared plus m squared plus omega naught minus omega. Now we use our 0th order expression in here. And this should be times omega naught, shouldn't it? Ooh, that might be a little too rough to write out. So let's check on how Mathematica is doing. It is still running. Great. I might need to stop running OBS if I want this to run faster. Yeah. Okay, well, in not too long, I'm going to have a full desktop rather than just trying to stream from a laptop, so hopefully it won't be an issue trying to, do my research while having OBS up and streaming. So I'm looking forward to that. All right. Thank you.